Calculating voltage drop for parallel conductors requires specific considerations. The equivalent resistance must be determined. For parallel conductors, the equivalent resistance is calculated using the formula 1 divided by rec equals 1 divided by rho plus 1 divided by R2 plus all the way to 1 divided by Rm, where rec is the equivalent resistance and rho, R2 through Rn are the individual resistances of the parallel conductors. The voltage drop for parallel conductors is then calculated using the same formula as for a single conductor. That is, voltage drop equals I times rec, where voltage drop is the voltage drop, I is the current flowing through the conductors, and rec is the equivalent resistance. Yes, when calculating voltage drop for parallel conductors, you use the resistance of the parallel wire size. This is because the parallel conductors have a combined resistance that is lower than the resistance of a single conductor of the same size. Now let's shift the focus to determining power factor. The power factor is a measure of the phase difference between voltage and current in an alternating current circuit. It is calculated using the formula power factor equals real power divided by apparent power. Real power is the actual power consumed by the circuit. Apparent power is the product of voltage and current. You can measure the power factor using a power factor meter or calculate it using the phase angle measured by an oscilloscope. The standard power factor for many industrial applications is 0.85 or 85%. This is because at this power factor, the circuit is operating at near unity efficiency, minimizing power losses due to phase differences. However, the power factor can vary depending on the type of load and operating conditions. When dealing with parallel conductors for electrical installations, understanding voltage drop is crucial to ensure efficient and safe operation. Several factors must be considered, including conductor size, length of run, applied current, and the type of material used for the conductors. Firstly, it's important to determine the appropriate conductor size based on the ampacity requirements of the load it will serve. The National Electrical Code, specifically Table 310.15.16, provides ampacity values for various conductor sizes and insulation types. For example, a copper conductor with THHN insulation may have a different ampacity rating than an aluminum conductor with the same insulation type. Secondly, the length of the conductor run plays a significant role in voltage drop calculations. Longer runs result in increased voltage drop due to the cumulative resistance of the conductor over distance. Therefore, it's essential to accurately measure the length of the circuit from the power source to the load. Thirdly, the amount of current flowing through the conductors directly affects the voltage drop. Higher currents produce greater voltage drop, so it's imperative to calculate the expected load current accurately. This can be determined using the power equation power equals voltage times current, or by referring to the nameplate data of the equipment being supplied. Finally, the material of the conductors, whether copper or aluminum, influences the voltage drop. Copper has lower resistance than aluminum for the same size conductor, resulting in less voltage drop. NEC Chapter 9, Table 8 provides resistance values for different conductor materials, which are essential for accurate voltage drop calculations. To calculate voltage drop, the following formulas commonly used: voltage drop equals 2 times the length of the conductor run in feet times the current in amps times the impedance per foot divided by 1000. The impedance value is obtained from NEC Chapter 9, Table 9 for alternating current systems. Once the voltage drop is calculated, it should be compared against the allowable voltage drop limits specified in the NEC. Typically, the NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. If the calculated voltage drop exceeds these limits, a conductor size must be increased to reduce the voltage drop to an acceptable level. For parallel conductors, where multiple conductors are used to supply a single load, the voltage drop calculation is slightly different. In this case, the equivalent impedance of the parallel conductors must be determined before calculating the voltage drop. To find the equivalent impedance of parallel conductors, the following formula is used: 1 divided by the equivalent impedance equals 1 divided by impedance 1 plus 1 divided by impedance 2, and so on, where impedance 1, impedance 2, etc. are the impedances of the individual conductors and parallel. Once the equivalent impedance is calculated, the voltage drop can be determined using the same formula as before, but with the equivalent impedance value. In addition to voltage drop, it's also important to consider other factors such as conductor dating due to ambient temperature and the number of conductors in a raceway or cable. NEC Table 310.15. B3. Provides adjustment factors for ambient temperature, while Table 310.15. B2. Offers adjustment factors for the number of conductors in a raceway or cable. These adjustment factors must be applied to the conductor ampacity to ensure that the conductors are not overloaded and that the insulation temperature limits are not exceeded. Moreover, proper installation practices are essential for minimizing voltage drop and ensuring reliable performance. Conductors should be installed in accordance with NEC requirements, including proper termination techniques and support methods. Loose connections and inadequate support can contribute to increased voltage drop and potential safety hazards. When selecting conductors for electrical installations, it's also important to consider the environmental conditions to which they will be exposed. Conductors installed in wet or corrosive environments may require special insulation or protection to prevent deterioration and ensure long-term reliability. The NEC provides guidelines for selecting conductors for various environmental conditions, including wet, dry, and hazardous locations. Furthermore, it's essential to maintain accurate documentation of all electrical calculations and conductor selections. This documentation should include conductor sizes, lengths of run, voltage drop calculations, ampacity dating factors, and any other relevant information. Accurate documentation facilitates future troubleshooting and maintenance activities and ensures compliance with regulatory requirements. In summary, calculating voltage drop for electrical installations involves several considerations, including conductor size, length of run, applied current, conductor material, and environmental conditions. By following the guidelines and formulas outlined in the NEC and adhering to proper installation practices, it's possible to minimize voltage drop, ensure efficient and safe operation, and comply with regulatory requirements. Understanding power factor is also essential for optimizing electrical system performance and minimizing energy costs. Power factor represents the ratio of real power to apparent power in an alternating current circuit. Real power, measured in kilowatts, is the actual power consumed by the load, while apparent power, measured in kilovolt amps, is the product of voltage and current. A power factor of 1 indicates that all of the apparent power is being used to do work, while a power factor of less than 1 indicates that some of the apparent power is being wasted due to reactive loads such as inductors and capacitors. Reactive loads cause the current and voltage waveforms to be out of phase, resulting in a low power factor. Inductive loads, such as motors and transformers, cause the current to lag behind the voltage, while capacitive loads, such as capacitors and electronic devices, cause the current to lead the voltage. A low power factor can have several negative consequences, including increased energy costs, reduced system capacity, and voltage drop. When the power factor is low, the utility company must supply more current to deliver the same amount of real power, resulting in higher energy bills for the consumer. Additionally, a low power factor can overload transformers, conductors, and other electrical equipment, reducing their lifespan and potentially causing premature failure. To improve power factor, several methods can be employed, including installing power factor correction capacitors, using synchronous motors, and optimizing load management. Power factor correction capacitors are devices that store electrical energy and release it back into the circuit to counteract the effects of inductive loads. By adding capacitors in parallel with inductive loads, the power factor can be improved, reducing the amount of reactive power flowing through the system. Synchronous motors can also be used to improve power factor. Unlike induction motors, which operate at a lagging power factor, synchronous motors can operate at a leading power factor, which can offset the effects of inductive loads and improve the overall power factor of the system. Optimizing load management involves reducing the amount of reactive power consumed by the system by minimizing the use of inductive loads and ensuring that equipment is operating at its rated power factor. This can be achieved by implementing energy-efficient practices, such as using variable frequency drives to control motor speeds and replacing old, inefficient equipment with newer, more efficient models. To measure power factor, a power factor meter or analyzer is typically used. These devices measure the phase angle between voltage and current and calculate the power factor based on this measurement. Power factor meters are available in various forms, including handheld devices, panel-mounted meters, and online monitoring systems. The cost of improving power factor depends on several factors, including the size of the load, the existing power factor, and the method used for power factor correction. Power factor correction capacitors are relatively inexpensive and easy to install, making them a cost-effective solution for improving power factor in many applications. Synchronous motors are more expensive than induction motors but can provide additional benefits such as improved efficiency and speed control. Optimizing load management involves implementing energy-efficient practices, which may require some initial investment but can result in long-term cost savings. In addition to reducing energy costs, improving power factor can also improve the reliability and performance of electrical systems. By reducing the amount of reactive power flowing through the system, voltage drop is reduced and the capacity of transformers, conductors, and other equipment is increased. This can result in improved system stability, reduced equipment downtime, and increased overall system efficiency. Power factor correction is also important for compliance with utility company requirements. Many utility companies impose penalties on customers with low power factors, as it increases the burden on the utility grid. By improving power factor, customers can avoid these penalties and potentially qualify for rebates or incentives. In summary, understanding and managing power factor is essential for optimizing electrical system performance, minimizing energy costs, and ensuring compliance with utility company requirements. By implementing power factor correction measures, businesses and homeowners can reduce their energy bills, improve the reliability of their electrical systems, and contribute to a more sustainable energy future. Considering these parallel conductor voltage drop factors, understanding power factor and how to measure it is key.